Hey, good morning. Welcome to a dreary Wednesday. I'd like to continue on here and get a couple more modules up for you guys so that we can wrap up close to wrapping up chapter 9. Okay, so we ended with the definition of the linear momentum. And the linear momentum was defined as the object's mass times its velocity. We discussed its units. We discussed the vector relationship between linear momentum and the velocity. And again, I want you to appreciate here that it is a vector quantity. Okay. So let's go back to Newton's second law. Which we know is F net is equal to mass times acceleration. This time, however, I want to write F net in terms of the change in the velocity with respect to time, because that's what the acceleration is, the instantaneous acceleration. And so if we look at the linear momentum, and if we take the time derivative of the linear momentum, and again, mass is constant in this discussion, then we get that the change in the linear momentum with respect to time is equal to the object's mass times the change in its velocity with respect to time. And so we can see straight off then that we can recast the net force in terms of the change in the linear momentum with respect to time. Okay, so so that's probably closer to how Newton thought of it. Acceleration really wasn't thought to be an important primal parameter in Newton's time, but to Newton in particular, the linear momentum, the object's mass times its velocity, carried actually some great importance. As a matter of fact, for Newton, mass times velocity was actually called the vis viva. In Latin, this meant, among other variants, it meant life force. So remember, as we said before, that these folks were steeped in both religion and philosophy, and so even though they were pushing the frontiers of physical science, it was certainly embedded in a fabric of philosophy and oftentimes religion. So for Newton, mass times velocity was the vis viva, or life force. Okay, so let's go back and let's look at the linear momentum. Linear momentum for a system. For a system of particles. Okay, we can't forget the picture that we developed earlier, right? And it's not a picture that's prominent in your textbook, but here's mass 1, mass 2, mass m sub n, and here's coordinate r1 in 3 dimensions, r2, r sub n. And each of these objects could be moving with the velocity v1, v2, v sub n. Okay, so if we look at that, then we're gonna call capital P, uppercase P, the linear momentum of the system, and that's just going to be the vector addition of all of the linear momenta of all of the particles in my system. And so we can just write it like that. Now, please, again, bear in mind that, when we talk about the system in this particular case, right, we're talking about this entire assemblage of objects or particles. And so we're talking about more than one object now, okay? And so this then is going to be then M1V1 plus M2V2 plus dot, 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 plus M sub n, V sub n. And this together then is going to be, if we look back in our previous lecture, this is going to be capital M, the sum of all the masses, times V for the center of mass. Okay, so then the total linear momentum of the system, uppercase P, is going to be equal to the total mass times the velocity of the center of mass. Okay. And now if we look at the time derivative of that, we look at the time derivative of the total linear momentum. That's going to be capital M, since total mass is a constant. So it's going to be V center of mass, so the time derivative of the velocity at the center of mass with respect to time. We recognize this, right? We recognize this as Newton's second law for the center of mass. Okay, so then dP dt is equal to capital M, A, center of mass, which now is going to be equal to F net for the system of objects. Okay, so at the end of the day, what we have here then is that we have for a multiple particle, or a multiple particle system. And that's really crucial here. It's going to be hard to get your head around that, but I'm going to do some examples as we move through this. For a multiple particle system, F net now, which is the net external force on all of those particles, a vector sum, is going to be equal to the total mass times the acceleration of the center of mass, which is going to be equal to the change in the linear momentum for that system with respect to time. Okay, so now if the sum of the forces, external forces on all those particles is 0, then we have 0 is equal to change in P with respect to time, and this is capital P, uppercase P. Now, the only way that can happen, only way that time derivative of the total linear momentum can be equal to 0 is that if the total linear momentum for that system of particles is a constant. Okay, so that now, as you're going to see, is our second important conservation law. So this is going to be called the law of the conservation of linear momentum. Okay, because when we say that something is constant, that is that it doesn't change in time. Doesn't change in time. Then we say that that quantity is conserved. And so we have the law of the conservation of linear momentum. Okay, so that's our second really important conservation laws. And again, as this discussion unfolds, I know it's been a little abstract up to this point, but I'm gonna do some examples probably in the next module. But I just want to finish. I want to finish one more conceptual piece here before we start to put all of this to work for us. Okay. So linear momentum is used often in multi-particle systems, and oftentimes ones that undergo collisions. So what is a collision necessarily? So it is the interaction. Is the interaction of two or more objects or particles that involve large forces, and that's relative. It's a relative term. Large forces over short periods of time. And that's a relative phrase as well. Okay. So so if you look in your textbook, the classic figure that they show is a baseball bat hitting a baseball or softball. It's hard to tell. It looks a little big, so I think it's a softball. And so they discuss that process in some detail. Okay, and so let's take a look. Let's take a look at that with regards to our new recipe for Newton's second law. Okay, so if we were to look at a baseball bat colliding with a baseball, a golf club, right, coming in contact with a golf ball, a tennis racket coming in contact with a tennis ball. If you're into billiards, hitting the cue ball into another ball, all those represent sort of macroscopic, real world collisions. Cars colliding into other cars, right? These are all examples of collisions in the real world. So you can well imagine that the forces involved in those collisions, they're not constant over time, right? They vary. As a matter of fact, if you just look at that picture of the bat colliding with the baseball in your text, you can well imagine that the force is going to develop over time. It's going to get very large at some moment in time, and then as the ball recoils off the baseball bat, that force is going to then decrease. Okay, so the forces involved are actually functions of time. They're not constant. Okay, and we can still write those as the change in the linear momentum with respect to time. And again, this is lowercase p now, because in the case of the textbook example, we're looking at just the change in momentum of a single particle, right? Baseball, golf ball, tennis ball, right? Something of that nature. All right. So we'll go back to a lowercase p designation. So we can rearrange this. This is then going to be dp. It's going to be equal to f of t dt. And then we can, to get a better mathematical handle on this, right, we could integrate both sides. Okay, we can integrate both sides from some time initial, some time 1 to time 2, time final, some time initial to some time final. And this side's easy, right, because we know that the integral of a differential is just the function itself. And so this b then becomes p, right? And p is actually going to be a function of time as well. T initial, T final. And so this is going to be P at T final minus P at T initial. Okay. That's easy part. This side, however, right, this remains an integral unless we know the mathematical form of the force as a function of time, which is usually very complicated, and we don't have that knowledge. But we give this a name. We call this the impulse. We give it the letter designation J. So the change in the linear momentum, because this is linear momentum final minus linear momentum initial. And again, I should have been a little bit more precise here. These are vector quantities, as we know, okay? So this then is going to be the change in the linear momentum is going to be equal to the impulse, all right? And physicists give this a special name, right? This is going to be called the linear momentum impulse theorem. Okay. And if we were looking along just one dimension, if we were looking along just the x direction, okay, x direction, for instance, and again, that baseball bat colliding into the baseball could very well be thought of during the collision as just occurring during the x direction. Then this becomes then the change in px is equal to the impulse in the x direction, and then this would be p final in the x direction minus p initial. Oops, p initial in the x direction is then going to be equal to the impulse in the x direction, okay? And so going back to the integral representation of that, then this is going to be the integral from some time initial, time final. This would be some f of x. Again, this is a function of t, dt, all right? And we know from a geometrical point of view that the integral of a function actually represents the area under the curve, right? So this actually represents an area under a curve, Okay. So if we were to plot, right, if we were to plot the force, say in the x direction as a function of time versus time, say for the baseball bat colliding into a baseball, okay? And so if you're looking right down, if you were looking right down at a baseball bat, so here's the baseball bat, and then, you know, here would be the baseball, right? So the baseball gets deformed, right? So it gets actually deformed as it comes into contact with the baseball bat. And again, if we're looking just at the forces, right, just at the forces on the baseball, right, and these forces then would be in this direction, then we could well imagine, right, that naturally they would start off at 0. As the baseball comes in contact with the baseball bat, they would become very large, and then they would trail off, right? So there's what the force as a function of time would look like. And that's a complicated function, right? We don't know what that function looks like. So we can't go back and do this integration straight off because we don't have knowledge of the force as a function of time in a mathematical form, okay? But we do know that the impulse, we do know then that the impulse is represented by the area under this curve. Okay, so this would be the impulse. All right. So what we do then is we say, well, you know, we can replace this complicated force behavior with a rectangular plot, and then this would be then some F average. And if we actually determined the area under this curve, that is in this triangle, or I'm sorry, this rectangle, then these areas would be the same. Okay, so these areas are equal. Okay, so then that integral can be replaced. Okay, that integral can be replaced. So T initial, T final. And again, this would be, again, T initial. This would be T final. This complex force can be replaced by some F average. Which actually, as you can see, is constant, right? So F average is a constant value. Right? It's a constant. So then that integral becomes then T initial. Oops. Let's get rid of that. Since F average is constant, F average comes out of the integral. This is going to be T initial, T final, dt. I can even integrate that, right? Again, it's the integral of a differential. And so then this becomes F average. Then this becomes T between T initial and T final. And then this is going to be then F average T final minus T initial, which is going to be equal to F average times delta T. Now remember what that integral is equal to, right? That integral is equal to J. And we know, going back upstairs here, right? We know that delta P, in this case delta Px, is going to be equal to J. And so then what we get then is that since J is equal to F average times delta T, in this case we get delta Px is equal to F average delta T. And I should denote this as F average in the X direction. Nothing magical about X. This could have been along Y or it could have been along Z. Okay, so again, if we wanted to go back here and just keep our example of the baseball bat colliding with, or the baseball colliding with the baseball bat, then again, remembering our picture, these are just going to be forces in the X direction during collision. Okay, if the baseball bat is hitting the baseball along the X axis. Okay, so this then becomes useful. This then is in a useful form. This is in a useful form. All right, beautiful. So the next time that we meet, I'm going to do some examples, and then we'll talk about elastic and inelastic collisions. We'll give you a couple of examples of conservation of linear momentum, and that will signal pretty much the end of the chapter. So hopefully next time we meet here on Zoom, recorded Zoom, the abstract work is done, and I will just work on some examples. All right, very good. Have a nice day, guys. All right, take care.